I'll begin with a word of prayer. Heavenly Father, we thank you again for this day. I thank you for this class, and just pray that you be with us. Help us to glorify you what we do, and just pray that we'd resolve any questions the students might have about this material. Lord, in your name I pray, Lord Jesus. Amen. If this thing will work. So I hope you're able to do some of these problems. I mean, I think a lot of these problems we have done things like them in class, right? But there is a problem or two here which is kind of sort of new. Let's just talk through the solution here. So first of all here, if I have log of x plus 2 plus log of 17, so I combine those to give me 17x plus 2 inside the log, then this goes in the denominator because there's a minus here. And this multiplication by 3 becomes power 3 up here by the properties of logs. And that's it, all right? So any questions about that one? No. So I just posted this solution in Canvas. My apologies about the 11 up here. I'm just recycling this solution from like last semester. So like last semester it was quiz 11, but for you guys it's quiz 9 as it happens. In fact, last semester in the spring, I think I gave this as a take-home quiz. So I really haven't given you guys much time for it, but I hope you have understood something you're stuck on, right? That's kind of the point here, because the next test will be somewhat similar to the quizzes that I have given since test 2, right? So like test 3 covers the material after test 2 up to the end of the course. It's not really comprehensive so much as it is focused on the last third of the material. Then the final exam, on the other hand, is comprehensive. It covers test 1, test 2, test 3. And there is some review for the final in mission 3. So I don't think those kind of problems are indicative of what I'll do for the most part on test 3, all right? You'll know them when you see them. So here I have a sum for the product upstairs, and then there's a minus because it's a division by x plus 7 inside the log here. So by properties of logs I get that. In the middle, natural log of the exponential, well that is inverse function, so that just brings down this 2 times x minus 3. Over here I bring the 3 out by the power property of the log, and that's about all there is to say there. Any questions? Now, we probably have not spent enough time on graphing logs in here yet. I'll try to pick another day and do a few more examples on these. Probably not today. We'll just talk about this one. Both of these graphs can be obtained from the basic graph of the exponential and the basic graph of the natural log shifted. I shift the exponential graph 2 units vertically to get this picture. I shift the log graph 6 units to the left to get that picture. Notice that there's a vertical asymptote for the log. It's moved from the y-axis where it usually is when we don't have shift here over to -6, because it's this +6 moves the vertical asymptote for the log over to there. And for this other one, there's a horizontal asymptote. If we just had like y equals 3 to the x-axis itself serves the role of a horizontal asymptote for the graph of y equals 3 to the x, but since we have +2, it pushes the horizontal asymptote up 2 units like that. I think about it that way anyway. So there you go, there's the graphs. I don't typically ask this question on the test in this format because it's just infinitely easier to grade the multiple choice version of this question, right? And it kind of tells me more or less about the same, what you guys know. Problem 4. I don't think we've done much exactly like this, but it's certainly within your, should be within your powers if you've understood the things we've done in here so far. I can't just hit this with natural log to start with. Like when we look at, so I'm looking for the time when a of t is equal to 6. So I put 6 is equal to 5 plus 2 e to the minus 0.3t because that's the formula that's given. I need to solve that for t. So one wrong thing you might be tempted to do is just to take the natural log of the equation to start with, because we've been doing that a lot, right? Like so many equations I've solved lately by just hitting the equation with natural log and then nice things happen. I can't do that here though, not immediately. I have to isolate the exponential first. So I subtract 5 to the other side. That gives me 6 minus 5, which is 1. And then I divide by 2. So this is how I get 1/2 is e to the minus 0.3t. Now that I've isolated the exponential, now it is time to take the natural log. Take the natural log of this equation. I get log of 1/2 is equal to log of e to the minus 0.3t. But remember, natural log and exponential are inverse functions. So essentially these cancel and leave us with minus 0.3t. And then solve for t by dividing by minus 0.3, which gives us log of 1/2 divided by minus 0.3, which is about 2.310. Any questions? Comments? Concerns? Conundrums? Nothing? All right, fine. I feel like there's not enough discussion in this class. I should add an essay. No. That would... No? Yeah. Did someone say yes? He'll be in the hall for his beating after class. What's that?
We can have regular conversations with you.
Regular conversations. But I like to talk about math.
We can talk about
that. I have bad news for you. We don't.
Yeah, I know. That's why I love my job. This is really the only way in my life that I can gather together a group of people and talk about math. If I try to do this in any other circumstance, they leave. But you are a captive audience. It's wonderful. Yes?
If you ever make us write an essay, can it be about why x keeps trying to get us to find y?
Why x cubed?
I think that joke was backwards.
I don't know. It's something like that. I don't know.
This class is a very rough audience. I should warn you. They're very demanding. Well, I have said very high quality jokes in here, so I've set the standards very high. You guys are so mean. Anyway, so natural 2 to the x equal to 5. Let's solve that. Now we're going to hit natural log. There's no sum or anything. We just natural log this thing, and take the natural log both sides. I get log of 2 to the x equals log 5. You can pull the x out by the power property of log. I get x times log 2, and then solve for x. Woohoo! About 2.32. Anybody solve this a different way? Yeah.
Log base 2.
Log base 2. Excellent. Now your answer looks really different, doesn't it? Let's look at his solution. So he was like 2 to the x equals to 5. The natural enemy of 2 to the power x is log base 2. So I log base 2 this equation, right? And good news, log base 2 of 2 to the x is x. And so there you go, answer. Now you might say, wait, but how's that go? Because the answer was log of 5 divided by log of 2. How are these answers? Change of base formula. That's right. Yeah, I think I've seen that joke before, like find x, and then like the cartoon is like, is it just an arrow? It's like it's right there. It's like right, you know. But I can't set that joke up. I can't set that joke up either. Natural log of 2. Like there's a class I like to teach here, and it's no small part of why I like to teach it is because about 80% of the way into the class, it sets up this like partially racist but really hilarious joke that is deeply inculcated in the mathematics of the course. So it's a great joke. If you're a math major, come take complex analysis, you'll find the joke. Yeah.
I remember the joke correctly now. Why does math keep trying to get us to find its x?
Why did Matt what?
Why does math keep trying to get us to find
This
its
guy's
x?
just so funny. I don't like.
Go on. Go on. Is this a Taylor Swift joke?
No.
Oh.
Because algebra is always trying to find x. Why does math keep trying to get us to find its x?
Ah.
Where did you get the y in the first place? Bro, my head hurts every day. I have no brain cells.
So these are the same answer. And just like you're saying in the back, this is the change of base formula. If you work that out, log base 205 is about 2.32 if I see it right. Problem 6 here. Problem 6, we have the natural log of a sum. Excuse me, the sum of the natural logs is equal log 3. So we use the property of logs. Natural log of a sum of natural logs is the natural log of the product. All right. And when I do that, I can use the one-to-one property, or if you like, I could exponentiate the equation. However you want to slice it, we get to x minus 1 times x plus 1 equal to 3, which then, putting everything to one side, as is our custom because it's a quadratic equation, x squared minus 4. But hey, that factors x plus 2, x minus 2. So we get minus 2 or 2. But minus 2 doesn't work, because if we go back to the original equation, the domain does not allow for minus 2 as a solution. Because if you plug minus 2 into the original equation, you get log of a negative number, which, since you guys won't let me teach you complex analysis, we're not allowed to do. That would get us about 20% of the way towards the joke, I'd like to say. But just like the natural log negative, like log of negative numbers. What, no? No? All right, fine. Yes, we've covered this already. You guys won't let me do calculus. All right. Does this make sense? Do you understand why this is extraneous? It's because we cannot plug a negative number into a natural log, all right? Moving on here. These ones are always a little bit tricky. I had somebody in the other section today get this right for about 3 simultaneously wrong reasons. Like they got the solution natural log of 4 equals to x from making a sign error and from making up a law of algebra which is not true. Would you like to see what's not true? Yeah. All right, because we don't spend enough time. I usually spend time showing you right steps, right? But it's probably also good to show you some wrong steps, just cautionary tales. So what I can't do here, check this out. So here's what the student did in the other section. He's like, okay, I'm going to natural log this thing. So here we go, natural log. Natural log of e to the 2x minus 3 times the natural log of e to the x equals natural log of 4. That was basically what he did. See this? This we cannot do. Natural log does not work this way. The natural log of a plus b is not equal to the natural log of a plus the natural log of b. That just is not how it works. It is true that the natural log of a times b, and it's easy to understand why students make this mistake, right? Because this is true, and it does look an awful lot like it, doesn't it? But there is a very large difference between a product inside the natural log and a sum inside the natural log. Barring some sort of just bizarre, really fortunate occurrence, there's practically nothing. I cannot remember in the thousands of hours of math I've done as an adult ever finding a way to simplify the natural log of a sum of 2 things. Like, there is no nice way to simplify this, generally speaking. Natural log of a product, on the other hand, is the sum of the logs. That's a basic law of logarithms. So you see this wrong solution he has here? It's based on this idea that the natural log of a sum is the sum of the natural logs, and that's just not true. All right? So let me just let us put a circle around it. Let's put a cross through it. Put another cross, and maybe some more. You get the idea. Don't do this. All right? Any questions? Comments? Concerns? So I have posted the solution in Canvas. Let's look at some problems that we haven't done yet. All right, so example 1. Suppose you're trying to solve 7 to the x is equal to like 3 to the kx. Find k such that. the above holds for every x. In other words, find k such that this is an identity. Any ideas how we do this? Thank you. What do you guys think? What should we do? Anybody? Give up? Yeah. All right. How about this? We'll take the natural log of both sides. See what happens. So if we do that, that gives us x log 7 is equal to kx log 3. I want this to hold for all x, right? So I can divide by x, and I haven't lost anything. If you like, logically speaking, you could put x equal to 1. That has to be, if this is true for all x, it's certainly true for 1. So from this, I get log 7 is k log 3, which then gives me that k is apparently the natural log of 7 divided by the natural log of 3. There you go. Does that make sense? Or, I mean, it's a different kind of problem, right? There's a few problems like this. That's roughly speaking problem 103 in the mission. Let me do a problem that's sort of kind of like problem 104. Example 2 here. What if you have p of t is equal to, say, 20 e to the minus 4t, and you also have that p of t can be written as 20 times 1/2 to the t divided by tau. So here tau is a Greek letter, right? So the question is to figure out what tau should be such that, you know, this is two different ways to write the same formula. So we're trying to, the goal is to find tau. So what do? I will set the formulas equal and try to solve for tau. So I've got 20 e to the minus 4t is equal to 20 times 1/2 to the t divided by tau. So the first thing I would do is divide by 20, you know, because I can. Then what happens? I've got e to the minus 4t is equal to 1/2 to the t divided by tau. Now what can I do? Any ideas? Nobody? How about we take the natural log of the equation, right? If we take the natural log of both sides, then that gives me minus 4t is equal to t divided by tau times the natural log of 1/2. Can you guys tell me how to simplify the natural log of 1/2? I mean, we should do that. What is the log of 1/2? Notice that the log of 1/2 is the log of 2 to the minus 1. So it's minus the log of 2. So what we have here is minus t divided by tau, natural log of 2. Now this has to hold for all t. So we can divide by t, solve for tau. What do we get? Tau equal to? Tau is going to be equal to the natural log of 2 divided by 4. There you go. For this problem, that's what tau would be. What's the meaning of tau? Anybody? What happens if we plug tau into the formula? Like, what's p of tau? 20 times 1/2 to the tau over tau, which is what? Tau over tau is 1, right? If I plug in tau for time, I get 1/2, right? So I get p of tau is 10. If I plug in 2 times tau, I get 20 times 1/2 squared, which is 10 over 2, which is 5. If I plug in 3 times tau, I get 20 times 1/2 cubed, which is 5/2. So what happens, every time we go forward a time increment of time tau, we're going to half the value of what p is, right? So it's called the half-life. This is the kind of formula that you would come up with in like an example of like radioactive decay, or perhaps like the number of bacteria in a petri dish, something like that. There's like a signature half-life where, you know, half of the bacteria die in that amount of time, and if you let that same amount of time go by, another half of the remaining bacteria die, and so forth and so on until it's mostly dead, right? Yeah? Any questions? So that's that. Now another example, probably our final example for today, because this one's going to take a while. Does everybody have the middle board? Because I want to work on the middle board here. If I want to erase. So have you guys ever heard of Newton's law of cooling? Newton's law of cooling? No? Newton's law of cooling says that the rate of change of the temperature of an object is proportional to the difference between the temperature of the object and the ambient temperature, or the room temperature. And if you take that differential equation and you solve it, you get the following formula. So Newton's law of cooling implies that well, I'm using K for the temperature. The temperature at time t, K, is equal to R plus A e to the minus lowercase kt. So here, this is the temperature at time t. This is the room temperature, which we take to be constant, A, and this is a constant, and this K is also a constant. So this is the model which Newton's law of cooling gives you. For example, if you had a cup of hot tea or coffee or something in a room, you know, how that cools will be according to a formula like this, basically, to a good approximation. All right? Now, if you look at this formula, there's a lot of moving pieces in it, isn't there? I mean, you've got room temperature, you've got this constant A, and you've got the constant K. So, like, I think of it this way. The A essentially has to do with what the initial temperature, let's say, the cup of coffee has. The R, of course, is room temperature, all right? And that K, the lowercase k, has to do with how quickly the coffee is losing temperature, okay? So, for example, K would be different if you had, let's say, an insulated coffee cup versus, you know, a not insulated one, something like that. So let's work a problem. Let's make up some numbers here. So let's assume that room temperature is 60 degrees Fahrenheit. That would be nice, wouldn't it? And your coffee is, let's say, 110 degrees Fahrenheit at initially, time 0. And then the coffee is, let's cool to 90 degrees Fahrenheit after, let's say, how many minutes do you guys want to make it? We can make it whatever you want. 15? All right. 15. And so this is, we're assuming that we're working in minutes, okay? Okay, and then I can ask the following question. How long until coffee cools to, let's say, 80 degrees Fahrenheit? There's a problem like this in your homework. It's roughly speaking, well, it's not roughly speaking, it is problem 101 is pretty much this problem. I changed the numbers and stuff, but here it is. Okay, so let's get started. Solution. To start with, I'm going to put in what I'm given, which is room temperature, right? So we don't need to do any kind of fancy math for that. We just write it down. K of T apparently is 60 plus A e to the minus KT. All right, since room temperature is 60, we have this. Now what? Now I can, so I use this information, right? Check. Let's use the next piece of information. The 110 degrees Fahrenheit, 110 is equal to K of 0, temperature times 0, which would be what? 60 plus A times e to the, well, e to the 0, which is 1, right? So 60 plus A. Oh, hey, we can solve that, right? We can solve that. If we got 110 is equal to 60 plus A, what's that tell us A is equal to? (110 minus 60, 50). A is equal to 50. A is equal to 50. Okay, so if you're keeping track here, we know that the K of T is equal to apparently 60 plus 50 e to the minus KT, right? So that's where we are at the moment. We're still missing, so now we've done what? We've used the second piece of data. Check. We use the second piece of data. We have a third piece of data that we should use, namely that the coffee is 90 degrees at 15 minutes. So now we'll put that in. Put that in. We'll get 90 is equal to K at time 15, which is going to be 60 plus 50 times e to the minus K times 15. Well, look at what we have now. We've got one equation that involves K alone, right? So we can solve for K. This gives me 30 is equal to 50 e to the minus 15K. Divide by 50. We get 3/5 equals e to the minus 15K, right? Because 30 over 50 is 3/5. And now take the natural log of this equation. We've got the natural log of 3 over 5 is equal to minus 15K. So lo and behold, we figured out that K is apparently equal to the natural log of 3/5 divided by minus 15. It may be convenient at this point to find a good decimal approximation for that value to use for the rest of the problem, okay? Now when you do this, don't be too sloppy. Well, it won't hurt my class because I don't use electronic homework, but if you were in a different class where there was electronic homework and you were sloppy about this, it'll make the rest of your answers wrong, right? So I'll try to be somewhat careful to be a good example. So natural log of 3/5, I divide by 15. Oops, better divide. I was subtracting. That would be bad. Divide by 15. So my k is about minus 0.0340, and I'll go that far. All right? So what does this all mean? This means that we have now obtained the formula that the temperature at time t is equal to what? It's equal to 60 plus 50 times e to the minus k is apparently, oh my bad, I'm sorry guys, that's not a minus, that's a plus. I lost a minus in my calculator. K is positive here, but there's a minus in the formula, so it's minus 0.034055 times T, all right? That's the temperature of the coffee at time T now, going forward, okay? So then what? So there's another version of this problem where I can say, find the temperature at time T for the coffee. If that was the question, then we'd be done. But it's not, so we're still up, you know, still got work to do here. And so what do we do next? Oh man, I'll try to hurry, sorry. We set that equal to 80. So next up, we solve 80 is equal to 60 plus 50 e to the minus 0.34055t. The solution to that gives me the time when the temperature of the coffee drops to 80 degrees. So I subtract 60 to the other side, that gives me 20 over 50 equals e to the minus 0.034055t. Take the natural log of this, we get t is equal to the natural log of 2/5 divided by minus 0.034055. And so what that is, Twenty-six point 26.52 minutes. That's how long it takes for the coffee to cool. So depending on the wording of the problem, it takes an additional 16 minutes past the 10-minute mark, right? But from the time we initially take the coffee and set it on the counter, 26.52 minutes, given the data that we have. Yep. Anyway, see you guys. Thank you.